Alright, so in the last video we were working on this paint mixture problem. At this point we have one equation here, our total amount equation. Then we also have a red equation. Now if you understand this red equation, you can probably see where we're going, because I can also write a green equation and I could also write a blue equation. So I could write for the green, and this is going to be how much, just like the red equation, it's going to be how much green is contributed by each paint. So 1/4 of the reddish paint is green, 2/3 of the greenish paint is green, 1/5 of the bluish paint is green, and together that has to make up 40% of 50 gallons. So that's 1/4 R plus 2/3 G plus 1/5 B equals, and now I've forgotten it already, 40% of 50. So that's 0.4 times 50. Now, and here's where you might get a bit confused here, because you might just say, okay, well, I'll just keep on writing equations. But I want to point out that we actually have 1, 2, 3 equations now, and we have 3 equations and 3 variables. So that is sufficient. We do not need to write the 4th equation. The 4th equation would be the blue equation, and you'd write it exactly the same way. You'd use these numbers and that 25%. But the thing is that we've already encoded all the necessary information in these 3 equations, so having a 4th equation will actually be redundant. Another interesting thing about this is that there are 4 possible equations we could write. Four possible equations. Any 3 of them will work. So I happen to use this one and then the greenish and the reddish, but I could have just used the reddish, greenish, and bluish, the red, green, and blue equations. Or I could have used the blue and the green and the number 1. Any combination of 3 equations from these 4 will give me the same system. Okay. The answers might be in a different order, but they will be the same values. So now it's a matter of writing down the matrices and kind of collecting all this information. This first one, and just to give you a quick overview of this, our first coefficient matrix is going to be 1, 1, 1, 50. Our second coefficient matrix would be 1/2, 1/6, 1/5, and that's 0.35. Let me make this a bit larger. Oops, that's not what I meant to do. I'm trying to make the window bigger. Well, anyway, make it smaller. How about that? 1/2, 1/6, 1/5, 0.35 times 50, 1/4, 2/3, 1/5, and then, I'm sorry, I got a bit ahead of myself. My coefficient matrix is just these numbers on this side, and then I'll have a constant matrix which has these numbers. So let me go to the slide where I've got all this information tabulated. Okay, so here's my system, and here's my matrix system down here. And this is the matrix that we need to enter into the calculator. Well, this one, and then invert it and do the multiplication. So here you see that, well, first we enter the matrix, then we enter the 3x1 matrix. Now in this case, actually what I would probably do for my 3x1 is I would just enter it like 50, and then this was, I've forgotten already, it was go to my whiteboard. 0.35 and 0.4. Okay. So you can actually just type in that, times, and it'll do the multiplication within the matrix for you. But other than that, oh, and I guess also be careful that there is. I'm going to do the inverse of that. Let me go to the next slide. So this is the inverse of matrix A times B. But essentially, it's the same sort of the solution. Once you get to the system built, the solution is the same method. Type in the matrices, take the inverse of the coefficient matrix, and multiply it by the constant matrix. Okay. There is your final answer. Okay, let's look at another chemical equation problem. So our method of solution is going to be similar to the other one. So just remind yourself, when we were balancing a chemical equation, we first wrote down the general equation with the reactants on one side and the product on the other, and then we put variables for the number of molecules of each reactant and product. We chose a target, and then we wrote equations, sort of atom equations or element equations, for the number of atoms of each element. So we're going to do that here too. So our general equation for this is photosynthesis. We've got CO2, and we're going to have X molecules of CO2 reacting with Y molecules of water to give me, and I'm gonna choose glucose to be my target. 1 molecule of glucose, and I do need a third variable, Z molecules of oxygen. So this is a little bit harder because we have 2 products and 2 reactants, and therefore I do need 3 variables. I don't want 4 variables. I want this to be my target, and so that'll be the thing that I'm trying to make 1 molecule of. And then we'll write equations, our element equations, which is the number of atoms of each element contributed by each molecule. We'll have one for carbon, we'll have one for oxygen, we'll have one for hydrogen, and what else do we have? Carbon, oxygen, hydrogen, and that's it. Okay, so let's write our carbon equation. And remember, the idea here is how many carbon atoms are contributed by each molecule. So the first one, CO2, has 1 carbon and then X molecules, so that's 1X. Plus, from water we have 1 oxygen times Y molecules of water. And that equals 6 times 1 is 6, and no variable there. And 2 times Z. So there's our carbon equation. Our oxygen equation, similar. I think I just messed up. For some reason I started counting oxygen in the middle of that. So let me fix that. I'm sorry. Let's do that again. So carbon. 1 carbon, no carbons, 6 carbons, no carbons. Okay, I apologize. Let's do oxygens now. 2 oxygens, 1 oxygen, 6 oxygens. And when I say 1 oxygen, 1 times Y is what I mean. 2 oxygens times Z. And then finally hydrogen, none. 2, 12, and none times Z. And there's our system. Now it's unorganized, so we need to move all the variables over here and then keep them in the right order. So we'll do X, Y, Z. So I need to move and leave these on the right hand side. Let me go to the next slide where we actually do this. So we need to move the Z's to the right hand side, and let me just quickly compare that with the, so this should go over here would be 0, then -2 and 0 again. Okay, and then we had this X 1, 2, 0, just double checking that we haven't messed anything up. 1, 2, 0 and 0, 1, 2. Okay. Alright, so there's our system. So really not that bad once you get the hang of it. Then we want to turn this into a matrix system. So our matrix is 1, 0, 0, 2, 1, -2, and 0, 2, 0. Then we'll have our variable matrix and finally our coefficient matrix. And then we can enter this into the calculator as matrix A. This will be matrix B, and so this is what we're going to do the inverse of. So as usual, we go to second matrix edit, make sure it's a 3 by 3, enter the values, then exit, go to matrix B and enter those values as a 3 by 1, and then finally take the inverse of matrix A times matrix B. And in this case, we get that we have the same number of molecules of each reactant and product that will produce exactly 1 molecule of, what was it? We were making glucose, right? Is that right? Yeah. Yeah. Glucose. Okay. Okay, so that's a slightly harder chemical equation problem. And remember to actually solve this, what we do in the end is go back and put this into the equation. So this is still 1, the other ones are now 6. We did potentially have the issue of getting non-integer values for any one of these. If this would have been like a third or something, then we would have had to multiply through and clear the fractions. So don't forget about that scenario. All right, I think we have one more chemical equation problem to look at. Let's do that in the next video.